So today we're going to be doing geometric pattern recognition. Now this is going to be implicitly different than arithmetic because what we're going to notice is that the change between terms is going to be constant multiplication or division. Unlike with arithmetic, when we add or subtract something each time, geometric means the population is either doubling, tripling, quadrupling, many different things can happen. So let's take a look at the first one. So the first one, what we're looking at from first to second to third is it looks like we have a petri dish with a number of bacterial colonies going on. So let's go ahead and label these. In the beginning, I see that I have one colony, then I have two, and then this one I have 4 colonies. So in between each one, I'm not checking to see whether or not I'm adding or subtracting. I'm going to check to see whether or not I am multiplying or dividing. And so 1 times what gives me 2? Times 2. And then from 2 to 4, I'm getting times 2. We can implicitly know that this is not an arithmetic pattern because if I were to try and figure out what the difference by adding or subtracting, I'd notice that I would get a +1 and then I would get a +2, which signifies that it is not arithmetic. In this case, we're multiplying by 2 each time, therefore we're going to get a geometric pattern. So if I were to draw the next 3 parts, what I'd have to do is I'd have to go ahead and say, well, if I know that I'm multiplying times 2, and times 2, that must mean that my next pattern has 8, 16, and 32 colonies in there. So I'm going to have to draw a petri dish with 8. So I'm just going to go ahead and say 1, 2, 3, 4, 5, 6, 7, 8. I'm not going to draw them just like that. This makes it a little easier to count. And then my next one is going to have 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And my last one is going to have 32. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 19, 20, 21, 22, 24, 25, 26, 27, 28, 29, 30, 31, 32. 32 colonies. Perfect. So we notice the petri dish as it's going up is going to be doubling in value each time. Okay. And not only can be going up, we said it can be multiplying or dividing. We can go from something like 4 pizzas to 2 to 1. So if I take a look at these values and I say 4 to 2 to 1, I know that with addition and subtraction, if I tried to do that, I would say, okay, I am subtracting 2, I'm subtracting 1. Because this is not consistent, I'm not arithmetic in nature. I am, however, checking out that I am dividing by 2 and dividing by 2. And now remember, with geometric patterns, I can either say that this is a divide by 2 or I can say this is a times 1/2. Either way, the pattern is going to be the same. And we're going to see that later on, the multiplying by 1/2 is probably going to be an easier way to do things. Okay. So that means in my next sequence, if I continue this, I'm dividing in half again, in half again, and in half again, which is going to lead me to here being 1/2. Half of a half is a 4th, and half of a 4th is an 1/8, which means I'm going to have 1/2 of a pizza. I'm going to have 1/4 of a pizza. I'm going to have 1/8 of a pizza. We notice the pizza steadily gets smaller and smaller. So if we move into some of the other examples that we got going on here, let's take a look at what are the next 3 parts of the sequence. So for my first example, I'm going from 1 to 10 to 100 to 1,000. If I were to try and figure out what I'm adding, again, I noticed that it wouldn't be consistent. I'd be adding 9, adding 90, adding 900. So again, arithmetic is out the door. We can't do arithmetic. We can do geometric because 1 times what gives me 10? Okay, this is going to give me a times 10 times 10. Perfect. That is consistent. So I know that my rate of multiplication is times 10. Okay, so that means I'm going to multiply 1,000 times 10, which is going to be 10,000. Multiply that times 10, I get 100,000, and then 1 million. And those are my next three terms. Likewise, if I look at this one, I notice that my numbers are getting smaller and smaller and smaller. So I could, albeit, say that I know that I'm multiplying by a 1/10. I could say that I'm dividing by 10. What we're going to do is we're going to keep with the rate of change on this one. So in this case, I'm not adding or subtracting the same thing. I'm not even going to try for this. But I do know in this one, I'm going to be multiplying by a 1 on the top. So times 1 up top, because 1 turns into 1, turns into 1. 1 turns into 10, turns into 100 on the bottom, just like what we saw up here. So it's going to be 1 over 10. 1 over 10. That means my rate is going to be 1/10. Perfect. So if my rate is 1/10, that means my next number, the bottom number, gets multiplied by 10. So 1 over 1,000, 1 over 10,000, and then 1 over 100,000. Next three terms. Boom. Okay. So what I want you to try is I want you to try the next one. Pause the video and pause when you're done and see how well you did. Perfect. So let's take a look at what's going on here. Now these three numbers, I can't see something intuitive like this. Now what I could do is I could do one of two things. I could convert these all to fractions and work that. But an easier way to figure it out is, how about we look and see 3 times what gives me 0.09. So an easier way to think of this is to take 0.09 and divide it by 0.3 and see what we get. So let's pull out our calculator. So we're going to say, okay, 0.09 divided by 0.3, and we get 0.3. Okay, and then we're going to do that again for the next set of terms. And I'm going to say 0.027 divided by 0.09 is going to be equal to, so 0.027 divided by 0.09 is again equal to 0.3. Okay? And what this means is it's a quick and easy way to figure out what that rate of change is by taking each term and dividing it by the term before. Okay. In essence, 0.3 times what gives me 0.09? 0.3 times 0.3. There we go. So my rate is equal to 0.3. Okay. So now what we can do with that information is we can move on into the next few terms. So I'm going to take my 0.027 and multiply it times 0.3. So let's bust this out one more time. Oop, wrong way. Here we go. So I have 0.027 times 0.3. And I get 0.0081. Multiply that times 0.3. And I get 0.00243 times 0.3. Ooh, and I get a really big decimal. So in this case, I have, let's see, I move it over and I'll have 3 extra zeros. So 1, 2, 3, 7, 2, 9. And those are my next 3 terms. Okay. So if we look at number 10, what we'll realize is that in number 10, we've got a similar situation as we did previously. We have to convert these into something that I can work with. So I'm going to convert 1, 10, and 100. Once I convert the words into these things, I see it's a very similar question to right here. So I'm going to go through and real quickly, I'm going to say, okay, 1 times what is 10? 10. Or if you wanted to do it similar to the method before, I could take the second term and divide it by the one previous. So 10 divided by 1 gives me what? 10 divided by 1 gives me 10. I could take the second term and divide it by the first. 100 divided by 10 will give me 10. Either way, if you can spot it or if you need to deduce it, r equals 10. Oop, I almost fully boxed that up. That'll allow us to figure out the next three terms. So 100 times 10 is 1,000, 10,000, and 100,000. Perfect. There we go. Okay. So what I want you to try is I want you to try the next two. Try number 12 and number 14. Pause the video, unpause it when you're done, and see how well you did. Okay. So now that you've had a shot, let's take a look at what's going on. So on number 12, I have a number, -1, 2, -4. Okay. So what you'll notice in this one, first and foremost, is that my values went from a negative to a positive to a negative. And what does that mean? Well, let's see. If I go for the first term, I know that 2 divided by -1 is going to give me a -2. And to find the rate between the second two terms, I know that -4 divided by a +2 is going to give me a -2 again, which means my rate is not a positive number this time, but a negative number. So every time I'm multiplying these terms, I'm multiplying by a negative value. Okay? So that means when I take -4, I'll get a times -2 will be a +8. Then I'll get a -16 and then a +32. But this isn't the right answer. This is just the values equivalent to the right answer. I need to put my answer in the same format. So in this case, I will get a 8, -16, and then a 32. And those are the next three answers in the same format as my original. Perfect. Okay. And if we look at the next one, we have a similar setup. I know that if I'm going from positive to negative to positive negative, what's going on is my rate is going to be a negative value right here. So I'm going to take the second value and divide it by the first and see what we get. -2. I'm going to take the second value, divide it by the one previous. -2. I'm going to take the second value, divide it by the one previous, and get -2. So I know my rate right here is, again, a -2. Okay. So that means my next three terms are going to be whatever -24 times -2 is, 48, -96, and then this one is going to be what, 180 plus 12, positive 192. There we go. Okay. And so the last thing that we see is, would we describe a geometric series as being convergent or divergent, and why? Well, let's take a look at some of our answers. Unlike an arithmetic sequence, what we're noticing is that sometimes if I have a rate that is positive, I notice my numbers get steadily higher and higher out of hand. If I were to look at the difference, we notice the difference went up and up and up, which means that this is spiraling up if I were to take a look at that. So let's say if r was equal to 10, I know that my pattern is going to look something like that. Conversely, if I have an r is equal to 1/10, what I notice is my value is getting smaller and smaller. So it's doing that. We notice that again with this one, it's again shrinking. So we've got that. When I have r is equal to 10, again, it's spiraling out of control. When I hit a negative value, a cool thing happens. Do we notice how with this one, if it's a -2, albeit my numbers are increasing, they're getting bigger and bigger and bigger in different directions. So if I have r is equal to -2, it got bigger, and it got bigger, 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 and we notice that this pattern is occurring. Conversely, if we saw one where the graph was negative and small, let's say r is equal to -1/2, we would notice the graph would be doing the same thing, but it would be doing a very different style technique. Okay. So sometimes my graph, if it's a 10 or a 1/10, so let's say if r is positive, it is neither, because it either curves up or down. Okay. We see the graph is either going up towards infinity or down towards a value. We could flip this upside down and it would be going down towards negative infinity or up towards a value, but again, we're not doing any sort of convergent or divergent behavior. However, if r is negative, we have a divergent property for large numbers. And for fractions, it's coming together. So convergent if r is small. So r is less than 1. And I'm going to put absolute value brackets around r because, again, we don't want to say it's between 0 and 1. This just will imply the absolute value of r must be less than 1. There we go. And why? Well, we've got a nice little visual aid of what's going on over here. Awesome. And so that's going to lead us into the types of graphs that we see. Now, what we see with geometric patterns is we see a shape that's called exponential growth or exponential decay. Keyword here being exponential. So, real quickly, let's go through one of the examples, just to get a quick glimpse of that. We already know that these are going to be exponential graphs or geometric. So what I know is that between each set, looks like I'm doubling, and I'm doubling. So my rate is going to be equal to 2. So we know from previously discussing this graph is going to get bigger faster. Secondly, we want to figure out what we need to scale. So I'm going to pick my biggest number, in this case 8, and I have 1, 2, 3, 4. I have 5 units. 8 divided by 5, if we take a quick glance at that on the calculator, what we're going to see is that 8 divided by 5 is going to be 1.6, which means that we're going to round that up to 2. So each one of these blocks we're going to count as 2. So I get 2, 4, 6, 8, 10. Awesome. The second thing that we're going to do is we're going to label this first, second, third, fourth, and fifth attribute. Now I'm going to take blue and we're going to graph this. So my first number is 1. My second number is 2. My third number is 4. And my fourth number is 8. So what we notice is going on here is that no matter what we try and do, I can't connect them all with a straight line. So if I connect these two with a straight line, I'm way off over here. If I connect the middle two, I'm off on the ends. If I connect the end two, I'm off. If I try and skip one, again, no matter how I work it, if I connect these two, there's no straight line anymore. Our graph is now curving. Perfect. So our graph, in this case, is going to have an increasing trend. Well, let's do this in blue. My graph is increasing because it's going up. But as we go up, I'm not converging on a number. You could make an argument saying I'm converging on infinity, but we're not converging. Diverging means my graph is going in both directions towards both infinities, which it's not doing, which means this is going to be a neither graph. And the last thing is, can we write an equation? Well, yes, we can. So the idea is, can we write an equation? So I got to come back all the way one more. I got to figure out, well, what would this number be right there? And I'm going to, let's do this in, no, I've already used red. Let's do this in purple. So my last number is 1. And if I'm multiplying by 2 each time, I'm going to take 1, I'm going to divide it by 2, which is going to give me 1/2. And so that 1/2 is going to be useful because our base equation for an exponential graph is going to be following this value. Y equals a times b to the power of x. Oftentimes, people put b to the power of x inside of a set of parentheses, or they'll just put the b inside the set of parentheses because we're not raising both a and b to the power of x, just b. So if I were to plug in my first number, if x is equal to 1, what I want to use is I want to use that starting value as a. So this is going to be y equals 1/2 times b, which is going to be my rate right here, which is times 2, raised to the x power. And let's take a quick look to make sure we get this right. So for my 0th term, so my term before I start, I'll plug in x equals 0. Anything to the 0th power is 1, which means it's 1/2 times 1, or 1/2. As I move over 1, if I plug in a 1, 1/2 is going to be times 2 one time. So 1/2 times 2 is 1. For the second one, 1/2 times 2 times 2, 2 times 2 times 2 times 2, 4, and that fits. And there we go. Awesome. So let's do another one of those. So for this one, again, my graph is going up. I've got 3 to 9 to 27 to 81. Let's take a look at what that would look like. So from 3 to 9, I'm multiplying by 3, 9 to 27, and 27 to 81. They're all multiplying by 3, so I know my r is equal to 3. Perfect. The next thing that I'm going to do is I want to graph all these numbers on this plane right here. So I'm going to take my largest number, which is going to be 81. I'm going to divide it by 5. And 81 divided by 5, let's see, that's going to be 50 is 10. It's going to be 16.2, which means I'm going to round that up to 17. So each value is going to be 17 total. So I have 17, 34, let's see, that's going to be 41, 51, 68, that's going to be 75, 85. Perfect. And I go through 1, 2, 3, 4, 5. Awesome. As I graph my values, I have 3, 9, 27, and 81. And again, we notice that no matter how we try and connect this, I'm not going to be able to draw a straight line because, again, when we deal with geometric, I kind of missed that one, but you get the point. When we deal with geometric curves or exponential curves, they're not straight lines. Okay, so I got to trace that back and figure out where that thing intercepts, which means I'm going to take the 3 and reverse it. So I'm going to take 3 divided by my rate is going to give me 1. So that value right here is at 1. My graph, again, is increasing. It's not converging on a single value. It's not diverging away between two. It's going to be a neither style pattern. And if I want to go ahead and write an equation, I know the equation is y equals a times b to the power of x. So I get y equals my starting value of 1 times my rate of 3 raised to the x power. And I could try out a few of these. So when x is 0, 3 to the 0th power is 1 times 1 is 1. Perfect. When x is 1, it's going to be 3 to the first power, which is 3, times 1, which is 3. Perfect. When I go to my second value, I should get 9. So 3 squared is 9, times 1 is 9. Awesome. So that all works out. Perfect. So I want you to try the last one. Give this one a shot. Pause the video, unpause it when you're done, and see how well you did. Okay. So now that you've had a chance to try it out, what we notice is this is one of those that I go from positive to negative to positive to negative because my rate is a negative number. It's -2, -2, and -2. So the number that I'm multiplying by is a negative value. That's going to mean something very different for when we graph this. Okay. The next thing is I'm going to take my largest number, which in this case is going to be a negative 40. I'm going to divide it by 5, so I'm going to get a negative 8, which means in this case I'm just going to deal with 8 up and down. So if I go 8, 16, 24, 32, and 40, 1, 2, 3, 4, 5, we're going to notice our graph does something very strange. Well, in the first one, I have a value of 5, and in the second one, I'm all the way down in the negative space. But by the third one, I'm back up here to 20. By the fourth one, I'm back in negative space. So how would I graph that? Well, don't even really know because that looks like just 2 points. I could move my axis up top, but let's see. So if I'm going down to negative space, let's just curve that down. And from 2 to 3, I'm coming back up, touching that value and going back down in negative space. And sometime after 4, I bet you I'm going to come back up sometime up here and go all the way up top. So what we see is part of a shape, and the shape that we're seeing is actually something that's doing this. And we notice all we're seeing is the top half of the shape. We're seeing the bumps, and the bumps are getting bigger and bigger and bigger. But there's an entire second half to this graph. So I want to figure out what this number is over here, which means I'll take my 5 and divide it by whatever my rate is. So negative 2. Or I'm going to get negative 5 halves. That's roughly equal to negative 2.5. Let's see. This graph, well, it's increasing and then it's decreasing, and then it's increasing and then it's decreasing. So it's not really doing those. It's doing neither. Or you could say it's doing both. If you wanted to, depending on the style questioning, if this was a multi-select, I would select both increasing and decreasing. However, the only option if this was a single select is going to be neither. It's not converging on something, meaning it's not getting closer to anything. This is going to be divergent behavior. We notice the graph is going in both directions, farther and farther and farther. So let's go ahead and write our equation. I need a starting value. In this case, I have this, negative 2.5, or I'm just going to go ahead and leave the negative 5 halves, because that's going to be a better form. My rate is negative 2, and this is where some people put the closing parenthesis. I'm going to put it around that. Just so you know, I'm not raising the 2 to the x, I'm raising the whole thing. Negative 2 is raised to the x power. Perfect. And there we go.